Right. So once again, you are welcome. And today is our lecture 2, limit state design. Last time, this is a lecture outline for today, and this is the lecture objectives. Since I've already shared, I will not need to go over. At the end of the lecture, these are the things I'm expecting you to be able to do. You should understand the ULS, SLS, apply partial safety factors in design, use code-based load combination, structure, you understand structural load path and decomposition, then calculate characteristics and design strength of concrete, and then you perform some structural load distribution calculations. Okay. So in lecture 1, we have already defined various terminologies and about structural systems and so forth. So this semester, as you are aware, is about reinforced concrete design. And we'll be designing beam, slab, column, foundation, probably stairs. And we'll be using British standards primarily for our design. And of course, you know that the British standard is based on limit state design philosophy. Now, it is important to note that in structural design, it will be more beneficial for students to be active rather than passive. Right? All students are admonished to consciously plan their studies and constantly practice by working more examples. So be a citizen, not a spectator. Quote and unquote, American president, not Akufo-Addo. Okay, so in this particular table, I have listed the codes and standards that will be applicable for our design. Again, it should be noted that these are not the only codes we use for the design, but these are the main ones we'll be referring to most of the time. And the first one here, I will entreat all of you, if you can print this one, BS 8110-1-1997, if you can print it, fine. If you can have it on your tablet, because I'll be referring to a lot of stuff in this code, and we have to go there and look for the information and use it for the design. So I wouldn't want to hear that I don't know about it, it's not with me. No. Any corner printing. Again, this code is what you are going to use in the exam hall. Okay. You need the code. Without the code, you can't even do the exam. So it's important to know. Just like you are using SMM7 for measurement. So this code here, the BS means British Standard. Then this is the actual code number, 8110. And the number here means the part 1, 2, 3, 4, right? And then the 1997 is a year of publication. So the part 1 of the BS 8110 is the structural use of concrete. The part 1 is code of practice for design and construction. Now, so this will be the base code. Then the second one, BS 6399, part 1, 1996, is for loading. So if you have to design, the structure is for a certain purpose, whether a classroom, a store, a residence, what's a hotel, and that's where you go to pick the appropriate load value for imposed loading. Then we also have 648, BS 648, 1964. This one, you have various materials, timber, concrete, plastic, whatever material we use in building. And it gives you their weight densities or unit densities, right? So based on that, you will be able to pick the weight of the various materials you'll be using, and you would be able to calculate their various weight or masses. And then BS 804, 1986. This code is for foundation. So if we are designing foundation, we'll be referring to this code. Okay. Then BS 44, 1997, specification for carbon steel bars for reinforcement of concrete. So the various steel reinforcement we use, how to do the scheduling, bending schedule and all that is provided, how to bend the bar, they are all provided in this particular code. And then the GS 1207 2018 is the Ghana Building Code, and specifically will refer to part 16, 17, and 18. Okay. And then what I call supplementary. Supplementary means there are other codes we may also refer to. So the BS 8110 is basically in three parts, but the part 1 is the base code. The other ones, we may refer to them where necessary. And then BS 6399 is also in three parts. So in due course, we may have to refer to any of them as may be appropriate. But remember that the first one here is the base code we'll be using. And all of you are expected to have it, whether you want to have it on your phone. But unfortunately, during the exam, you can't have it on your phone. You may have to have the full code for the exam. But for the purpose of learning, I'll reluctantly accept soft copies, but make sure it's available with you. And anytime we are doing something, you have to refer to it. Okay. So that's about the intro. So we start with the limit state. You remember we have done a bit of the limit state, which is a philosophy. And the main philosophy is that the structure will not become unfit for its intended purpose during its expected life. That's the main objective of the limit state design. So basically, the state beyond which the structure no longer fulfills the relevant design criteria is referred to as limit state. So as we have learned already, there are two limit states: ultimate limit state and then serviceability limit state. Because we've done this, I won't spend my time here. Now, the ultimate limit state is the state associated with collapse or with other similar forms of structural failure. So this state typically is something that can lead to collapse of the building. Okay. So in terms of ultimate limit state, the concern is safety of the people and safety of the structure. So some of the states include strength, overall stability, robustness, and special hazards, which I had explained in the previous lecture. So remember that the ultimate limit state, the concern is about safety of the people and safety of the structure. So when you are designing the structure, you make sure the structure itself is safe and the people that will use the structure are also safe. When this is done, then you say that you have fulfilled ultimate limit state. And what we look for? Strength. Strength means bending, shear, and the rest. Stability also is include robustness. I told you robustness means if one small aspect of the building collapses, it shouldn't lead to the collapse of the entire structure. And that will be disproportionate collapse, which is not acceptable. So I've kind of provided some explanation to the various ULS. Okay. So when it comes to strength, we are talking about the load carrying abilities or capacities of the various sections that are used for the structure. And I've already talked about stability and robustness in the previous class. Then the other state, which we had also spoken about, is serviceability limit state. The state that corresponds to conditions beyond which specified service requirements for a structure or structural member are no longer met. So here we are looking at more of the service requirement, right? So the serviceability is concerned with three major things. One, functioning of the structure or structural members under normal use. Two, comfort of the people and appearance of the construction works. So when it comes to serviceability, we are talking about the functioning and the comfort of the people, including appearance. But if we talk about the ultimate limit state, it's about the safety of the people and the structure. So that's the main difference. So some of the things that can lead to this more functioning or discomfort of people or lead to very poor appearance would be deflection, cracking, vibration, durability, fatigue, fire resistance, and lighting. So again, I'm giving a bit of explanation about each of them. Okay, and remember we have also done this in a previous class. Okay, so this has been summarized in this way. So what this here means is that under the ultimate limit state, if we talk about strength, we are talking about flexure or bending, compression, shear, torsion, tension. Okay, and then we have stability and robustness. And then if we talk about serviceability, examples we deal with is deflection, cracking, vibration, durability, fatigue, fire resistance, and lighting. So the what we are saying is that anytime we are designing, if we fulfill these things, we must make sure that if we want to fulfill ultimate limit state, we should make sure the structure is safe in terms of strength, stability, and robustness. But if we want to look at serviceability limit state, which has to do more with comfort and appearance and functioning of the building, we have to check the deflection, cracking, vibration, durability, and so forth. So these are some examples that we must fulfill or criteria we have to fulfill in terms of the limit state design. Okay. All right. Is there any question anybody want to ask? You can raise your hand and I'll allow you if you have a question. So we need to remember that in the design, if you are to design to fulfill ultimate limit state, it means you must make sure that your building is safe for the people and also the structure itself is also safe. Okay. All right, so we will look at the loading or loads. Okay. We know about dead load. That's the permanent weight of all the weight of all permanent elements. Okay, that's dead load. You have done it, so I don't want to speak too much. Imposed load has to do with the use and occupancy of the structure. If it is store, the imposed load is different from a classroom, is different from an office, and that is what you find in the BS 6399. We also have wind load due to wind effect, right? Then we have self-weight. I want you to take critical look at what we call self-weight and superimposed dead load. Self-weight is a dead load. Superimposed dead load is also a dead load, but there's a difference. So self-weight is actually the weight of the structural system. Okay, that is self-weight. That is self-weight. But when it comes to superimposed dead load, for example, if you take a slab, the slab is the structural element. But we do screeding, we lay tile, so the screeding, the tiling, the terrazzo finish, and all that, they are what we call the superimposed dead load. The plastering and so forth, the ceiling. Okay, let me leave the ceiling for now. But the plastering, they are all superimposed dead load. Okay, so usually you see that they are kind of finishing more or less applied to the structural elements. A local bond and code, they are all superimposed dead load, right? So let us note that superimposed dead load and self-weight, they are all dead loads. Then we have load case. So if we talk about load case, the main idea is that we have some compatible load arrangement or set of deformations and imperfections considered simultaneously with fixed variable actions, dependent action. So here we want to talk about individual loads that may occur on the structure. Maybe there's dead load, maybe there's imposed load, there's wind load, earthquake. These are the various load cases. So the various loads that you're expecting to act on the structure are considered under what we call load cases. Okay. Now, when it comes to, we have another one we call load combination. Here, what we are saying is that we have various load cases, but is it true that all the time, or if let's say we have a dead load, imposed load, wind load, will all the three be happening at the same time? The answer is no. Sometimes the three will be together. Another time, only one will be active. For example, if we take a classroom, if we are there learning, their load is already there, and then imposed load is also there. We are the imposed load, so the two is acting. If maybe there's a strong wind blowing, then dead, imposed, and wind load are all acting. If let's say we end our lecture and all of us will leave the classroom, you notice, and assuming we have also removed all the chairs and the tables, it means the only load that will be acting at the moment is dead load. Imposed load and whatever is no more. So in design, you try to do this and see which of these loads can be acting at the same time. And that's what we call the load combination. And it should be designed in such a way that any combination of these loads that may be acting at one point, the structure should be able to resist these loads. And then we have something we call design load. Okay. Then the actual loads have to be converted to design load by considering some factor of safety, that we call partial factor. So when it comes to design ultimate load, so the design load, if it is under the ultimate limit state, we call it design ultimate load. If it is under the serviceability limit state, we call it design service load. Okay. Then we have service load. In simple terms, the service loads are the actual loads. They are the actual loads without load factors. So the actual load, if the load that supposed to come on the building is 10 kilonewton, then that is the actual load. Then we have service load arrangement. Okay, so if you say load arrangement, the load have to be arranged in a certain way. For example, it is possible that, let's say you are going to write the exam in the Great Hall, and all of you are on the corridor and they are checking. So if they are checking, it means the inside there is empty, but the corridor is full. With some along the line, after they have finished checking everywhere, you notice that all of you are in the classroom and the corridor is free. That is the alternating way the loads are acting on the building. So one time the class will be full, the corridors will also be full. So this kind of simulation need to be done to ensure that in the event where these things happen, okay, the structure will not fail. For example, at the hostel, anytime they are playing games or they are doing a certain activity, you see that all the students will leave their rooms and they will now be on the corridor. So it means that the room there is empty, only dead load is active, but the corridor is now having a full dead load and full imposed, right? So when it comes to the load effects, the effects of the loading, bending moment, shear force, axial force, and so forth, that's the load effect. So we call something characteristic value. And I want to let you or remind you again that when it comes to the limit state is based on statistical values. So characteristic loads are normally thought of as the maximum load which will not be exceeded during the life of the structure. So what we're saying is that the load that we'll use to design the structure it should have only 5% probability of being exceeded during the time or the lifespan of the structure. That's the characteristic load. So if we are saying the imposed load is 3 kilonewton per meter square for a particular structure, what we are saying is that we are confident that 95% probability that that load will not be exceeded. And if it will be exceeded, it can only be exceeded 5% of the time. So remember that characteristic loads are the actual loads, which is the same as the service loads, okay? They are the actual loads. And because it's characterized based on statistics, we call it characteristics loads. Okay? Now, when it comes to loads that we use in design, I know you have done this in design 1. So characteristic dead load, we don't just call it dead load, we add the characteristics to it. And I want to emphasize here that you know that the word characteristic does not have an S. So if you add an S, you are in a different planet. There's no S, right? So characteristic dead load, imposed load, and wind load. Note it. I know you know this. That dead load is what? GK or small gk. Imposed load is QK or QK. And then wind load WK or small WK. Okay. Now note that these are the symbols you'll be seeing, and I don't need to tell you what they are again. What you should remember is that dead load is GK, live imposed load is QK, and wind load is WK. And usually the capital letters are used for concentrated or point load, whilst the small letters are used for distributed load, right? So when you talk about air load, if you have a retaining wall like this, okay, the soil at the back is a load onto the wall, okay? It's a load onto the retaining wall. So that's a typical earth load. And usually in design of foundation and retaining wall, you find this load. And then we have some load during construction. Sometimes you pack some materials on the building whilst you are doing the construction. After you are done the construction, those loads are not supposed to be there. We call them construction loads. And these are loads, if you don't consider in design, these loads can even lead to the collapse of the building during construction. Okay. Then we call something what a partial safety factor for loads. Anytime we are designing, if you want to calculate what we call design load, you must multiply partial safety factor, which is represented by gamma subscript F, by the characteristic load or by the actual load. Okay? When you do this, the answer you get is what we call design load. So anytime you are asked to calculate design load, it means the actual load you have, you multiply by the partial safety factor for load. And here you notice that the partial safety factor for load takes account of 1, possible increase in load, inaccurate assessment of the effects of loads, unforeseen stress distribution in members, the importance of limit state being considered. These are the reasons why we use the partial safety factor for loads. Okay? One of the exams I asked students to just provide reasons why partial safety factor of use, and people were just scoring 0 left, right, center. You see? So if there is increase in load, the partial safety factor will take care of that. So even though the load may increase within certain level, but the structure will still work, it will not collapse. So remember that the formula for calculating design load is gamma F times the characteristic load. Now, load combination. I want you to listen to this very carefully because This will underpin whatever we'll be doing in our design. Load combination means what and what load will be acting together at the same time. So if you look at the top here, we have the load type. We have dead load, imposed load, and wind load. Under the dead load, we have adverse and beneficial. Under imposed, we have adverse, beneficial. The adverse and the beneficial, they are always, but usually we focus on the adverse. There are certain critical cases you may have to look at the beneficial also, but let's look at the adverse first. If we are saying that dead load and imposed load will be acting together, which is the load combination, right? Which is the load combination. It means the dead load must be multiplied by a factor 1.4 and imposed load must be multiplied by 1.6, right? If we are saying dead load and wind load will be acting together, in that case, the dead load now will be multiplied by 1.4 and then the wind load will be multiplied by 1.4. If we have dead, wind, and imposed load, all of them acting together in during the same time on the structure, dead load should be multiplied by 1.2, imposed load 1.2, and wind load 1.2. And you can see some information that adverse partial safety partial factor is applied to any loads that tend to produce a more critical design condition. And beneficial factor is applied to any loads that tend to produce a less critical design condition at the section considered. And usually, our focus is with the adverse, but there may be instances where we consider the beneficial also, especially the dead load. If we consider beneficial, we call it minimum dead load, right? Okay. Do you have any question regards to this? This is the main thing, and you must know how to do load combination. No, you know that the usual thing, go over, I would never go over. What is it that you don't understand? Be specific. As for going over, it's out of my dictionary. You know it. What is it that you don't understand? Be specific. Any question regards to the load combination? Remember, we said load combination means number of the loads that will be acting at the same time. And don't say that their load is multiplied by 1.4. No. Depending on which other load that the dead load will be acting with, right? So in the case where dead, wind, and imposed are acting together, they are all 1.2. You can't say one is dead load is 1.4. No. Okay. If you have any question, you can lift your hand and then I'll answer. Otherwise, I'll proceed. Okay. Since the house is very quiet. Ima?
Yes, sir. Please, I want to ask that what is the role of partial safety factors in load combinations?
What is the rule?
Of partial safety factors
Did
in
you
load
see this slide? I explained this slide. Did you see this slide?
maybe.
Hello. No, it's
Hello,
not
sir.
maybe. I was here. I explained from here. So the reasons are here, 4 of them. I explained before I went to the load combination.
All right,
Come
sir.
again?
Please, thank you very much. Please, thank you very much. I've seen it now.
Okay. I saw another hand, but the person has put down his hand. Okay. So it means that Yes, Ben.
Good evening, sir.
Yes, good evening.
So I was a little bit confused about when you said when dead load and wind load, or the three loads all are acting at the same point, is 1.2 or something like that. I was confused over there. I couldn't get it well.
The first thing I mentioned was that limit state design is based on statistical values. So it's not just like looking at it and say 1. These factors were developed based on statistics of the event that has happened in the past. So the idea here is that if all the three are acting, then the effect of one of them may be reduced. So if all the three are acting, then the dead load should be multiplied by 1.2 as the gamma F. And imposed load should also be 1.2. And wind load should also be 1.2. So there's no rule that every dead load all the time is 1.4. That's not the rule. It's about which and what load are acting at the same time, which we call the load combination.
Okay.
Right?
Thank you, sir.
Okay.
Thank you, sir.
Okay, all right. Okay. Any other question? Okay. So once again, remember that the design load is the characteristic load by the gamma, and the gamma factor is what we just look at for loads. Okay, so whether it is dead load, imposed load, and wind load, they all have their own factor, as we have seen in the previous slide. So, for example, if let's say we are saying dead load and imposed load is acting, then here I'm calling in load combination 1, 1.4 GK, and the imposed load is 1.6 QK. If it is dead plus wind, these are the factors applicable. And if it is 3 of them, this is the formula you use to calculate the design load, right? And anytime we are referring to, please take note, anytime we are referring to minimum dead load, we are saying 1.0 GK, and that is a beneficial. So remember this. Minimum dead load means the beneficial dead load, which is 1.0 GK. So remember. And I mentioned again that usually the capital letters are used if we are talking about concentrated or point load, and the small letters are used for distributed loads. Okay? So the one we'll be using most is the first one. We'll be using this one the most because we are design, we will not do wind design, we won't do wind. So dead plus wind is out, dead plus imposed plus wind is out. Let's understand that we are learning. It's not like we are designing a life structure. No, it's a learning and it's a process. So our syllabus, we are not to do wind load. And doing wind load, that will be too much. Okay, so we'll be dealing with dead and imposed loading. Are we okay? All right. So remember this formula very well. That's what we're using. And I know you have used this formula in design 1. So if you don't know how it came by, here it is. But it's not something new anyway. Isaac.
Yes, sir. Please, what of the minimum dead load? Please, you said we are doing the dead impose, but without the dead wind and the dead imposed wind. What of the minimum dead load?
Minimum dead load can always happen, and you see where that will apply.
Okay, sir.
If there is a structure which doesn't have a dead load, then that must be an AI structure. I don't know how can we have a structure how can we have a structure which has a structure that has been built but doesn't have a dead load? Hey, I don't even know whether even AI structure will not have a dead load. I don't know. Okay, so dead loads there, they are permanent, they are always there. Okay, so what channel? Okay, we call something load arrangement. And this load arrangement, I want to use this diagram to explain it. As I explained earlier, if you have a classroom, there may be one point, everybody will be in the classroom. There may be another point, all the people will move to the corridor because there's something happening. Everybody wants to see it. And the classroom will become empty. There's another point where the classroom will be full, corridor will be full, everywhere is full. And that is this scenario. Okay? So we try to alternate and see if all the load is here, what happened? This one, we are saying if it is just one span, you have to put all the load. But here you see multiple span. These are support, multiple span being. We put the full 1.4 GK, 1.6 QK. And this one, we are trying to simulate the loading. Okay, let's assume that the first span is the full load. Then the next span, a small load, alternating load. Okay, then the following span, the full load, minimum load. So here, the third case can be like this. Okay, the third case, because I started with the full load for the second case, this one I'll now start with the minimum, then the full one, minimum, then the full one, like that. And look, analysis or design is iterative. So for example, this will be A, this will be B, this will be C. So we have to analyze all this. And then I'll look at case A. If I'm looking for shear force, A, B, C, D, where did I have the biggest value for shear force? I pick the biggest value. Maybe the biggest shear force may be here, or maybe in the B. I'll pick it. Then I'll do the bending moment. So I'll do the bending moment diagram for A, for B, and for C. And then I look for which one is giving me the worst condition. So basically, it's not just loading it one and then leave it like that. So we are saying that what if the loading regime changes? We still want to see the effect and be able to take care of it. Okay. So that is what we are basically referring to. That so alternative loading. The first case, the full thing is load combination one. Then the second case, the same BMO, you alternate the load. And then the third case, you alternate it. So you have to do this analysis of these three. And I believe you must have seen certain bending moment diagrams where they have done plotting of bending moment, different in the same diagram. And that is coming from this load arrangement. So we are not leaving anything to chance. Okay. So if we are designing, let's say, if mobile phone is being designed, they will design it in such a way that it is possible one day the mobile phone will fall into water. So it is designed in such a way, if it fall in water within certain minutes or seconds, and you're able to pick it, you salvage your phone. There may be another time you hold the phone and it will fall down. We say the level of impact should help the person to pick the phone back. If we design the phone and assume that nobody will ever drop his phone, then it means a poor design. So if one day somebody mistakenly, the phone falls from somebody's side, it means that at top FM there, you have to go and buy a new one. And that's a very poor design. So that's the same thing we are saying. It's not every day human beings will be in the room. They may be, sometimes you go into a particular lecture hall and you see that students have gathered in only a small part of the room and the rest is empty. And all these simulations have to be done. in design, so that we are able to take care of all the dynamics that will happen when the structure is in force. Okay, so that's about the load arrangement. Any question about load arrangement? Okay. So we look at what we call structural analysis. Now, after all this loading stuff, you have to do the analysis to get the internal forces and the moment and so forth. And basically, when it comes to reinforced concrete, they behave also as a rigid frame and should be analyzed as such. They can be analyzed as a complete space frame or be divided into series of plane frames. So the general procedure for a building frame is to analyze the slabs as continuous members supported by the beams or structural walls. So the slabs can be either one-way or two-way spanning slabs. Okay. So we should know that the columns and the main beams are considered as a series of rigid plane frames, which can be divided into two types: brace frames and frame supporting vertical load, that is on brace frame. And I believe you have done this in design 1, brace and unbrace structures. True or false? Just say the truth and shame the devil. True or false? True? Okay. Since I don't have any answer, I believe all answers are true. Okay. Now, so when it comes to structural analysis, we have done some in strength 1, strength 2, strength 3. And particularly strength 2, we learn about how to calculate bending moment, shear force, bending stresses in beams and all that. And then strength 3, you dealt with deflection of members and the Euler buckling columns and so forth. So there are several ways. You have the force method, flexibility method, displacement method, or stiffness methods, numerical and computational method. There are several ways that you can use to analyze the structure. And for the purpose of simplifying the design process, you may have some books that have also given certain arrangements and different kinds of beams and the loading arrangement. So they will provide some factors. If your beam look like that, you can use those factors to generate your bending moment and shear forces. And then it will save you from rigorous analysis and so forth. Okay? And I believe that you have also learned about what we call subframes. Subframes. Because if I have a tall frame like this, okay, let me add one. This being the columns, you have the beams. If we say subframe, I can single out, okay, a small portion of it. If I want it, I can just single out this part like this, okay, and I can sketch it like this. And then the beam is here. This is a subframe. So instead of analyzing the entire thing, which will be more difficult, I can break it down into small parts and analyze. Okay? So this is a rigid frame. And out of this rigid frame, for example, I can even cut a section here. So I can take the whole floor and then just cut the beams at the top. Like this. Right? Like this. And then this one will be easy to analyze. That's what we call subframe. So you may see this in design books a lot of the time. Okay. So yeah, that's about that. So as for structural analysis, typically you won't find, they may just state the method in the design code, but they will not give you that if you want to do matrix approach, this is the step. No, because they know that it's been covered most of the time in mechanics of materials, structural analysis books. So they may mention the type of analysis you can use, but they will not go further to specify the procedure for doing it. Okay. All right. So if you have any question, you may ask. Otherwise, I'm moving to material properties. Okay. We know that concrete, the reinforced concrete we want to do is basically concrete and reinforcement. So it's important to know the properties of the materials for the reinforced concrete. Okay. All right. So characteristic strength. Here, I want you to pay much attention and understand this once and for all. So if we say characteristic strength of concrete is defined as the value of Q strength below which not more than 5% of the test result may be expected to fall. So characteristic strength of concrete, which is the FCU, is the 28 days cube strength in Newton per meter square. Okay, so the minimum grade of reinforced concrete are given in table 3.1 of the code, and the grades are grade 30, which you normally call C30, C35, and so forth, which we'll look at very shortly. If we are saying characteristic strength, remember that we test concrete cubes. So what we are saying is that if we test 10 cubes at the lab, not more than 5%. Okay, let me put it. So let's say we want a strength of C30. If we test the cubes, the values you have for each of the cubes, 95% should be above 30. The result should be above 30. So if you have more than 5% falling below the value 30, it means your ratio is not good and it cannot be used to achieve this strength. That's basically the meaning. So that's the characteristic strength of concrete. And I want to let you know that when it comes to reinforced concrete, if it's a lightweight aggregate that I use, then minimum characteristic strength is C15. If it is normal weight concrete, minimum C25. So no, this is what has been specified in codes around the world. So C20 now, I just want to tell you, the so-called 1 wheelbarrow is to 5 wheelbarrow of sand is to 1,000 wheelbarrow of stone now we use. Ratio near tested concrete nuclear and do C15. Aye. And the moving year. You get it. So the concrete strength minimum is C25. And then we buy on seminar modern measure near na we are near man into moving ye. Alex.
Good evening, sir.
Yeah, good evening.
Yeah, sir, please, why is it that when casting casting suspended flow, sometimes they use, let me say, half bag of cement to mix the aggregates, but when casting a staircase, you see that they say they should raise maybe 3/4 of the cement so that that place will be rich.
That's the question I'm giving. Bruh, BBA ni wasa wati. BBA ni wasa. Said you hate TV and then this animal nam. We call something ratio and design strength. So if I specify that C25 must be used for the concrete, it must remain C25. And you must find a ratio which we call design mix. So you do what do you call it? A preliminary mix design, you have to do a mixed design and get the ratio that can give you C25. So after you go and crash in the machine, we will learn how to do the calculation of characteristic strength. Then you know that if the strength that you crash in the machine is within this range, then your ratio is fine. Then you use that ratio for the works. So there's nothing like halfback. That's what I'm warning you people about. That halfback and whatever is baseless. If it is 1:2:4, you must measure it as such. If you are using halfback, it must, and the ratio is 1:4, whatever, it must still remain in the ratio. But sir, 1 bag of cement is to 1 trip of sand now with munyai. Uahaka, amen. Munyai. Isaac.
Okay, sir, please. Sir, please, the 1 bag of cement and 1 barrel of sand. Does it really work to get the actual grade? Because I learned if you have to measure, let's say the same bucket of the cement should be the same bucket of the sand. But for the 1 bag of cement and a barrel of sand, I'm not sure it's like equal volume.
No, that thing can also be used. You just have to know the size of the barrel, the wheelbarrow, because the standard wheelbarrow is actually 4 headpans. So you should be able to know how many headpans makes up your wheelbarrow or makes a full wheelbarrow that you are using on the side. And we know that two headpans makes up a 50 kilogram of cement. So you should know how many headpans are within the wheelbarrow, and then you can also use that strategy to measure. But the kind of measurement, that kind of dariga measurement on site must stop. Because a lot of the structures we have tested, which has collapsed, some of them, they have not collapsed, they are still there like death trap. The concrete strength are mostly less than C15, and you only find few of them that are above C15, which is not even up to the C20 and C25. So it's a big issue. Okay. All right. Let's continue. So if you look at the BS 5328 Part 1, 1997, these are the grades of concrete specified in that code. Okay. So if here, so the C means compressive strength, right? And the value after the C means the actual value of the compressive strength in megapascal or Newton per meter square. So anything above this line is not for structural use. Usually, anything above here is not for reinforced concrete. Reinforced concrete starts from C25 down. Okay? So if C30 has been specified for the work, you must do mixed design. And based on the mixed design, you prepare cubes and go and test. And if you are going to prepare cubes, where you get material for the project, where you get the sand, where you get the stone, that's where you have to go to pick this material for the cube. And then you test. And after testing, you calculate the compressive strength. And then after that one, you can now check whether the strength has passed or has not passed. If the strength passes, you use that ratio you use to prepare the cube as the ratio you adopt for the works. Okay. Typically, if you have concrete strength, usually beyond 40 and co, you need special admixtures like water reducers and so forth to be able to make you achieve this strength. Because if you don't use admixtures, you may hardly achieve strength, particularly a strength of 50, okay, and more. Okay, so from today, know that anything below C25 cannot be used for structural purpose. In that case, reinforced concrete elements. Are we okay? Cannot be used for reinforced concrete. And this ratio I really want to do some research on that. Now, move prank forma. So when it comes to the reinforcement, the characteristic strength of the reinforcement is the same thing. So we are saying that the test results, not more than 5%, should be less than that. So let's say, if we are talking about mass steel, okay, which the BS 8110 recognized two types of steel, the hot rolled mass steel and then high yield steel, or hot rolled or cold work. Usually this one is R. The high tensile may write T, sometimes Y, sometimes H, and so forth. And the H is becoming common in these days. So if you see this kind of letters attached to the maybe 1601, you should know that we are talking about high tensile. Look at the strength. 460, about double of the 250, right? And in recent time, the 500 is becoming common because of the Eurocode standard. Okay, so it's like a double of the mass steel. So if you use mass steel, you need more of the reinforcement bars to do the same work. So it is not automatic that when you use mass steel, your work will be cheaper. It's never true. There are instances if you use mass steel, your cost will balloon. But if you use high tensile, you have an economic structure. So the idea that if you use mass steel, your cost will be lower than high tensile, it's neither here nor there. This must be properly assessed. There are some structures I'll use mass steel. Some structures I'll use high tensile, because if I use mass steel, I'm worsening the financial situation for the client. So I'll never use mass steel. If the client wants mass steel, I will demonstrate to the client. Because when you are designing, we do iterations and see which one is the most optimized cost. So when you talk about the reinforcement bars, so let's say if I test 100 pieces, and then I'm testing maybe mass steel, 250 strength. Only 5% of the result I will attain is expected to be less than 250. So if more than 5% is less than 250, it means that the reinforcement bar is bad and cannot be used for the project. Okay? I believe that you remember proof stress. Proof stress, stress 1, right? You remember proof stress? Yeah, it's in the design code. Okay? All right. Now, so this characteristic strength I'm talking about, like I said, I indicated earlier, when you have a project, what you do, we call something mixed design. You do the mixed design, and then you prepare cubes. Based on the cubes, you go and test. So let's say if we are C30 strength is specified for the work, you go and test the cubes. Remember that the material used to prepare this cube must be where you get material to do the project. You don't just go anywhere. The materials, if we will take sand from Amasaman, where we'll be taking the sand, we'll get that sand exactly for the test. After that, you prepare the cubes, maybe 7 days, 14, 21, 28, you cure all of them, you take it to the compression testing machine to test, and then you provide your results. And the compressive strength you get from each of the cube is not the characteristic strength. I'm stressing again, it's not the characteristic strength. If you want to get a characteristic strength, the result that you have had, if let's say if you test about 20 cubes. You have result for 20 cubes. So you use that data with this formula here, right? Fk is the characteristic strength. So you calculate the mean of all these values, 33, 34, you calculate the mean. And then you calculate the standard deviation. Come and substitute into this value, in this formula. The answer you get is what you must compare with the C30. And if that answer is equal or greater than C30, then the ratio that you use to prepare the cube, you adopt that ratio for the work. But if the answer is less than the C30, it means the ratio you have used is not correct. So you have to do a new mix design. And maybe if you have to replace some of the sand with a different material and all that, then you have to do. You get it. So this is the formula for calculating the standard deviation. And note that this is the sample standard deviation, not population standard deviation. So it's n-1. If you don't use this formula, you are out of order. And then this is how you calculate the mean. You add all, if it is 10 cube results, you add all the compressive strength, and then you divide by 10. If they are 100, add all the 100, divide by 100. You get the mean. So you should remember that the result you receive from the lab concrete test is not the characteristic strength. And characteristic strength is based on calculation. So when we receive test result from the lab, we have to do this calculation before we can now say that the concrete ratio is good or it's not good. You get it? Okay, and this formula is basically based on a 28-day strength. Okay? All right. Do you have any question? Yes. Yes.
Professor,
Yeah.
I've worked with some engineers, and what you're talking about, I've seen something. The kit that they will cast for testing, I've seen that they don't cast it for testing, but right now when they are working, they cast it in the concrete, like maybe they are casting the floor. Through that, they will cast the kit. So what is the advice for such engineers to?
Okay, what they are doing is correct. We first of all do mix design and then decide on our ratio before the work starts. While the work is ongoing, we do what we call confirmatory test to confirm that what we are expecting is what we are getting. So even if you have a ready-made concrete people to supply, we will take sample, and then because we have told them we want C30, they say we have agreed. So when we are casting, we'll take sample, cure it, go and test, and check whether indeed they gave us C30. If they did not give us C30, then any legal issue we can take. So that one you have been seeing is confirmatory test. You get it? It's confirmatory test, so it's not wrong. Let us also know that with time, companies may have taken material from different places, and they might have done their mix design over time. So they know what proportions, if the sand is for Amasaman, they know what proportions they need to have, okay, to be able to get a certain ratio. But during the actual work, there must be confirmatory tests, okay? So it's very important to know that. Are you okay? I hope I've been able to explain what you are asking for. Okay, let's proceed. Then remember, we have done partial safety factor for load. Now we want to talk about partial safety factor for materials. Okay, so whilst we have loads, we also have materials, and we must apply safety factor to our material. And material one is gamma M, while that for load is gamma F. Are we okay? Why do we use partial safety factor? For materials. And here I want Clue Emmanuel, to take note that this is explained before I give the factors. And this is to take account of the difference between actual and laboratory values. Because whatever you test in the lab, the difference will be different from the actual work you are going to do. The difference is clear. Lab results cannot be equal to the result we get from the field. 2, local weakness and inaccuracies in assessment of the resistance of sections. And 3, it takes account of the importance of the limit state being considered. So these are reasons why we use material partial safety factors. Okay. So in terms of materials, if it is reinforcement, the gamma M is 1.05. And you can find this in the code, table 2.2 in BS 8110. You can find this in the code. So if it is reinforcement, the factor is 1.05. If it is shear, you are dealing with shear strength without shear reinforcement. For concrete is 1.25. Bond strength 1.4. Concrete in flexure or axial load 1.5. Other one like bearing stress, they are all 1.5. So let's know that in terms of gamma M, material factor for partial safety factor for materials, these are the values that are needed. Note here carefully, if we are dealing with design strength, we are talking about material. Design load, we are talking about load. So design load, as we saw, is the characteristic load times the gamma for load. This time around, if you are talking about design strength, which has to do with the material, you divide by the gamma factor. Take note clearly. So if it is concrete, the formula for calculating design strength is 0.67 FCU over gamma M. And then FCU is the characteristic strength of concrete. Okay? And if it is reinforcement, the design strength is Fy over gamma M. Okay? And we should note all these things carefully. And from the table, we know for concrete is 1.5. And that will give us something like this. And we know if it is reinforcement is 1.05. So note, that of the material, the gamma is dividing it, whilst for loads is multiplying it. This we must note clearly. Okay. All right. Any question here? Any question here? Okay. These are things you should also partly know in design 1. Now, again, you see the stress strain graph, it has come back again. Yeah. So stress strain graph, wherever you pass, everywhere you go, there's stress strain graph. So this is the actual stress strain graph for concrete, this one. And for design purposes, it has been modified. It's been modified to this shape. So this one is a design strength, if you can see, 0.67 FC over gamma M. And then the maximum strain you expect to see in your concrete is this. And then you see that this is parabola. From here to here is parabola. So the strain at the end of the parabola is this value, right? And what you see here is the modulus of elasticity is the E. So this means that E for concrete you can use formula of 5.5 root SC over gamma M to calculate the Young's modulus for concrete. And that's what the code is giving. And this one is figure 2.1 from the code. Is that okay? And I want you to take note carefully of this one, that the factor of 0.67 that you see here, right, takes account of the relation between the Q strength and the bending strength in the flexural member. It is simply a coefficient and not a partial safety factor. This you must note. So don't ever think that the 0.67 FCU, the 0.67 here is a partial safety factor. No, it's a coefficient. It's not a partial safety factor. So if one day I ask you to calculate design strength of concrete, you see, you can't just say it's FC over gamma M. It's 0.67 FC over gamma M. And that's what you must note. And this is the stress strain graph for steel, okay? For reinforcement, this is how it look like. So this is the actual, and this one is the modified. This one is kind of a combined graph. This one here is if it is tested in tension, the behavior. And this one here, if the steel is tested in compression, the behavior. So it's like combined graph of tensile testing of steel and compression testing of steel. It has the same strength, both in tension and compression. And this one is actually figure 2.2. Okay, there's something. Figure 2.2 in the BS 8110 part 1 code. Okay, good. Do you have any question? And you see the reason why I expect you to read something before you come to class. You notice that if you had done that, your understanding will be completely different. Okay. So it's important to first of all know the behavior of the material before you start designing. Okay? Any question? Alex?
Sir, so how would the in case of the concrete, how would the graph look when testing for tension and compression?
No, as for tension, it doesn't even exist, Kra.
Yeah.
The tension does not even exist for concrete. You will not even reach anywhere. But there's a way of testing concrete in tension. Okay. There's a way of testing concrete in tension. Okay. But that one is totally different from stretching. It's completely different. How to test concrete in tension is completely different from the usual stretching of the concrete. No. Okay. But it's also tested in tension. But that graph does not even exist. Okay. Okay. That one the A2O. Concrete. Concrete, that graph, if you do it, will just be something like this. It doesn't even exist. Because the tensile strength of concrete is about 10 times, 1/10 rather, 1/10 of the compressive strength. So, but you can also research on how to test concrete in tension and you will see it. Okay, so structural loading. All structures are loaded. Is that okay? So let me go straight here. The loading on structures are based on scientific values. And so if we are going to put load on the structure, remember this table is very critical. If we are dealing with dead load, the self-weight of the member will use this code, BS 648 1964, which you must have used for design 1. And for spine post dead load is the same code. So this code you should be familiar for design 1. Again, if it is imposed load, for floor imposed load, is BS 6399 part 1. And if it is wind load, is the part 2 of the same code. And if it is roof load, is part 3. Again, this must have been known in design 1 already. So this, if you want, we are talking about the loading that you put on the structure. Okay, these are the codes you have to refer to. So for example, if the structure will be used as an office, you have to go into the BS 6399 part 1 and see what is the floor load for office. If it is classroom, you know. If it is bedroom, you go there and pick. And these codes I'll be giving them to you, or you can all download it yourselves. Because in due course, you have to refer to it to be able to use it for design. Okay. Then, when it comes to dead load and all that, I bet you know that. Now, in this code, the BS64, okay, this code, the BS648, is a code that comprises different materials and their weight, mass densities, right? So, if you remember, density is equal to mass over volume. No be so. So if I want mass, it's density times volume. So if I want the weight, what do you think? It's mass times what? Acceleration due to gravity. So this code comprises all, in fact, most of the materials, if not all, and their weight or mass density. So you can use this formula to calculate the mass. Then you multiply the mass by the acceleration due to gravity to get the weight of the material. And usually, though we know acceleration is 9.81, we usually use 10 meters per second square. But if you use 9.81 per meter square, meter per second square, you are not wrong. But typically, we use the 10, the approximated value. Okay? And the imposed load, I've spoken about that. So this table here is kind of some examples I've picked from the BS648. If it is reinforced concrete, what is the unit weight? Is here, right? And then if it is steel, if it is solid, this is the weight. If it is corrugated roofing sheet per mm thick, is here, right? If it's soft too, this is the weight. If it is, because don't forget, if we say load, we must know the weight. And this is how you use to calculate. So in that code, there are several materials listed and their weight. And you see rendering. If it's 13, 1:3, 30 meter cube, this is the weight. And screeding, this is the weight. Terrazzo, tiling finish, all of them, they are there. So depending on the material you are using for the structure, you go to the code, look for their weight, and use it to calculate their total weight onto the structure. Is that clear enough? Any question? Is that clear? Okay. So, floor load distribution. Let us know that I keep saying, if you are learning something, you learn the thing the right way. Learning the thing mutu there, it will not help. If you don't learn it the right way, so anytime you are doing the wrong thing and you are even confident that you are doing the right thing, no. So learning the right thing is the way to go. Okay? So when it comes to floor load distribution, in terms of beam and slab floor system, typically the loading may be uniformly distributed line loads, triangular, trapezoidal, and concentrated point load. If we say line load, if you have a block work, okay, block work on a beam, block wall on a beam, block wall is a line load, right? Even though it's a uniform distributed, it's just along a line. Okay, block work on the beam or on the slab, they are all line load, but they are all again uniformly distributed. Okay, all right, so let's look at something. Here, I want you to pay rapt attention because the beginning of design in terms of calculation is here. If you miss this one, you will see that the other part, you don't even get it. And I intentionally provided this slide long time ago in Bethlehem to you, so that you know this before we come here. So here, I'm only expecting questions, but people did not do. God willing, next week will come and I'll implement my rules. So in terms of beam slab system, if we say beam slab system, we are talking about a structure made up of beam, slab, column, beam, slab, column, beam. That's the common one we have in Ghana. So if you are workers, so it should be easy if you have the beam grid like this, right? This beam divide the beam here. So the slab defined by this is panel, even though we call it slab panel. I think I showed you last time when we met, slab panel. So if I have a slab panel like this, the longer side is called LY and the shorter side is called LX. You can't change it. The short is always LX and the long is LY. C'est fini? Now, the aspect ratio is that you calculate, take the longer side, divide by the shorter side. If the answer is greater than 2, we'll classify the slab as one way. If the answer is less or equal to 2, we classify as two-way. This is very easy. Do you understand it? Any question? Any question? Okay. So if you have understood this, then the next stage is that you now have to decide if it is one way, how is the load distributed? If it is two-way, how is the load distributed? So now you have been able to classify the slab into one-way, two-way, which should be the most basic thing you must do. Good. Then the next way is you find out how is the load distributed. So here, I believe you have been seeing these symbols in drawings. And here, I want to let you know, this is a slab panel, okay? This is a slab panel. That's this is a LX, LY. LX, LY. What is this symbol meaning? This symbol is showing the direction of the main reinforcement. I repeat, this symbol is showing the direction of the main reinforcement. So if you see this one like this, it shows one-way slab. This one shows two-way slab. So let us take note. And so I don't need to write whether it's one-way or two-way. The symbol should tell you. So this one is telling us the main reinforcement is in both directions. But if it is one-way slab, main reinforcement is only in one direction. And the main reinforcement must span the shorter direction, which is the LX. Take note. So that the distribution bars come on top, not the other way around, right? It should not be the other way around. Okay, so now we have classified, and now I have also shown you that in drawing wise, when you see this, it means one way. If you see this, it means two-way. And one day I can ask you, what is the meaning? What is the importance of the symbols in this particular two classifications? And you should be able to tell me. Good. So I think I've already spoken about it. And let's see here, load distribution. Again, this is very simple. And you have all the right reserve to understand this. Let's look at the diagram A, one-way slab. So first of all, we have looked at how to classify it. We've looked at how to indicate by symbol whether it's one-way or two-way. And the third one, if it is one-way, how should the load be distributed? And if it is one-way slab, it means you have to distribute the load to the longer side. So the arrows that you are seeing are the direction of load distribution. So what this means is that if you check and it's a one-way slab, if you check and it's a one-way slab, it means that divide the shorter side into two, like this. When you do this, all this part, the load goes onto this beam. Remember that this one, we are saying beam is all side, okay? Beam is all side. But because it's one way, we divide the shorter side into two, and then the remaining load comes here. So this beam here and this beam is essentially carrying the load. So this beam and the one here, they are free. There's no slab load on them. Stephanie, do you get it? Any question? Because you should be able to do this before you can now do your design. Ima?
Yes, sir. Please, for the one-way spanning slab, I want to ask that if this is the issue, how can we design our beams to be able to withstand the pressure that this one-way slab load distribution comes along with?
You first need to know load distribution. And then the rest is mathematics. If you do analysis, you get your bending moment shear force. If your analysis is right, your design will be right. Do you get it?
All right, sir.
So the first thing is understanding how the load distribution is done. Then your analysis can also be done well. If your load distribution is wrong, it doesn't matter the kind of analysis you do, everything is wrong. Okay. So are we okay with the one-way load distribution? So for example, if this side is 6 meters and this side is 2 meters, right? Then by the K will be what? 6/2, which is 3, and this is greater than 2. So we know it's one way. If that is the case, then we now divide the shorter side, which is the 2 meters, into 2. I'm stressing you divide the shorter side into 2. Then half of this load goes onto this, and half of this load comes onto this. And because it's like this, if I want to now sketch this thing, is like this, and then the load is a complete UDL. So when it comes to one-way load distribution, it's completely a UDL load. The kind of distributed load is uniformly distributed. Okay, so I think that everything is fine with that. Good. Now, let me go on to, if it is two-way slab, what do we do? If it is a two-way slab, then you have to look, the LS is always the shorter side and the LY is the longer side. Okay? So, if it's a two-way slab, once again, the shorter side might be divided into 2 like this. Then, what can you do? The shorter side again, you measure from the edge here to here, as you can see, half of the shorter side. And again, you see this place is also half. Okay, so if you draw this line, if you connect from the corner to hit this, corner to hit this, you get this triangle. And this angle will be 45 for you. Then you go to the other edge also. Okay, so remember that this one is half of the LX over LX. Okay, and the same half is measured here. Okay, so if I draw this line from here to hit this here and to hit this here, and then I'll get that. Then the middle part here, you join with a straight line. Okay, so here you notice that if I take this one from here to here to here is now trapezium, isn't it? So this load will now come onto this beam. Do you get it? And you see that this one too is trapezium. So this load goes onto this beam. And this one goes onto this beam, like that. There's no difficulty. So if I want to sketch, for example, this beam like BC, this beam, what I can draw here is like this. Draw this line. I have a support, okay? And the loading is like this, right? And it's like this. Can you see? And if I want to look at, let's say, AD, the beam along the AD, this is simply that beam. Okay. I just want to sketch here so that you see it. So if the support is here like this, it means it's a triangular load, okay? Now, when we were dealing with the strength 2, you notice there's some triangular load, trapezoidal load, that's where it's coming from. Okay? So when it comes to this particular triangular and trapezoidal, sometimes the analysis can be a little bit complex. So in order to make it simple, we do what we call equivalent distributed load. So in that case, you just calculate all the total load and divide by the span from here to here. And then you convert it to something similar to this. You get it? Good. So after you have done this, then now you are on the way to do your analysis now. So the load distribution is very important. So you should know that when you have your slab arrangement, the beam slab arrangement, you have to identify all the slab types and then check all their load distribution, right? And then indicate how their loads are transferred, and then you can now do the proper line diagram of this beam. So what is this about? What we are saying here is that we call something yield line. We are saying if this slab is to fail, if we put heavy load on the side, this slab is going to fail. The crack pattern in the slab will look like this one, to look like this. And that's the kind of analogy we are using to say this is how much load goes to this and goes to that. And in similar way, for simply supported way, the crack pattern will be like this. And half of this will fall off. This half will fall on this beam. We may also argue that, okay, if this is fixed beam, then part of it here will be small. But this is so small. So approximately, to simplify analysis, we just ignore that small triangle thing down because of fixity. But generally, this half one way will fail, and that is how two way will fail. Okay? So, any question? Any question? Okay. So if there's no question, that's good. Yes.
Sir, please, what if the slab is semicircle?
That is a complex loading. Okay, so in complex loading, you have to resort to the proper yield line method of analysis before you can, there's a way of sharing the load. Okay. But when you are learning design, you can't learn with semicircle. Oh God. So if it's a semicircle, there's a way this load, okay, can be shared. Okay. So that one is a kind of a complex system. And there's a table or there's a yield line procedure for some of these complex edges, that complex slabs. But please, let's understand from the basic rectangular slabs so that we don't confuse ourselves. If you have a square slab, if it's square, then at the end of the day, the whole thing will become like you cross it like this. So on all four sides, everywhere is a triangular load. Okay, based on this principle I've shown you. I want you to do this for me right now. If this side is, let's say, 7 meters, and this side is, or let me make it 6 meters, and this side is 3.5 meters, tell me whether the slab will be one way or two way. I will be with you shortly. Okay, there's a hand up here. Yes.
Sir,
Yeah,
please, it will be a two-way.
to be a two-way. Okay, that's fine.
Thank you,
Let
sir.
me, yeah. Hey, Ali, is this the same Ali I know? Ali, hey, Ali.
Yes, sir. It's the same
Right,
Ali.
where's my tundra?
So I'll bring it next week.
Otherwise, you get E with a broken leg, sir.
Oh, sir, easy,
Okay,
easy.
okay, you can ask your question.
Sir, it's a two-way
Okay,
to
good.
the answer.
So are things getting better for you?
Yes, sir.
Okay, Yanko, gradually everything will be fine. Okay.
Inshallah.
Okay, so Yentoaso. So load distribution onto columns and beams and okay, Mami. You see, sadly, matron baby, just for you to understand, that's all. But yeah, last time when we came for class, I told you that when we talk about primary beams, it means the beams are supported on columns. But anytime we are talking about secondary beams, it means the beams are supported on beams, right? Okay, so I hope Cindy is in class today. Today, if you miss the class, Wasuben Shipa. So if let's say you have column here, you have column here, you have column here, you have column here. All these beams, okay, are primary beams. If there's a beam here, okay, if there's a beam here, this beam is now supported on these primary beams, okay? So this beam is called secondary beam, okay? So every secondary beam will always become a point load on a primary beam. What am I saying? So if I draw a line diagram of this beam, because this beam is resting on this, if I divide into two, half goes here, half comes here, and it will become a point load. So this is how we get point loads also. And in turn, if we are dealing with this column, then half of this beam will become point load on the column, half will go here. So the load distribution in terms of beam to column or beam to beam, you divide it, half goes here, half goes there. You divide, half goes there, like that. You just divide into two, one goes here, one goes there. That is after you have distributed the slab loading. Okay, so what do we do if we are doing slab loading? We say classify the slab panels, indicate the direction of the load distribution, calculate the characteristic dead and imposed, calculate the design load based on the formula we have seen, 1.4 GK, 1.6 QK, and then calculate the area of the slab supported by the beam, and then calculate the total load distribution onto the beams, okay? And calculate the total load and equivalent UDL. These are just some steps that you can also follow and then do it at your own pace, okay? All right, so we all know that in terms of load distribution, the load is from the slab, it goes into the beam, and then from the beam to the column, and then from the column to the foundation to the natural ground. We know all this. So that's the principle of load distribution. Okay? All right. So if there's any question, I can address it. Otherwise, we'll start to work some examples. Okay, there's a hand up here. Yes.
Yeah, all right, sir. Please, I want to ask that, please, with the help of a free body diagram, could you kindly show me the difference between an EDL and an ECL?
And what?
An EDL and an ECL.
What is ADL?
Sir, please, when you were talking about the two-way spanning system, you said that the equivalent distributed load will be converted into an equivalent. You said an equivalent distributed load will be converted into an equivalent concentrated load. So
No.
I got quite
No,
confused,
no,
and I
no,
wanted
no,
you to
no,
show me
no.
a difference
I
between the two.
said triangular loads and rectangular loads, sorry, triangular, trapezoidal, convert it to equivalent distributed load. In fact, equivalent UDL. They are all distributed to simplify analysis. But you can go ahead and do the calculation for triangle or trapezium like that. But if you want simplified approach, typical for manual, you can convert them to. But we did this in strength 2, conversion into equivalent concentrated load. We have done that. So if you have forgotten, then you have to go back. But repeating it here may prolong the class for us. That's how we learn. If you forget something, no akofa. You got it? Okay. Okay, so let's look at some examples. Oh, the first example here, we have been given some samples that have been calculated from the lab. Okay, we have prepared some concrete cubes and then we've taken it to the lab to test. And cube 1, okay, cube 1, this is the size and this is the cross-sectional area, this is the maximum load, okay, and we have to calculate for the compressive strength, okay. That's what we have to calculate for, compressive strength. Are we okay? We have to calculate for compressive strength. We have to calculate for compressive strength. So with this question, as you see here, this is typically what will be done at the lab, and then they'll do the calculation of compressive strength, okay? Okay, all right, so let's see. So this is the question, and this is the given, and this is the solution. Simple crap. I did the way to me and your class. So you have cube 1, size linear, okay? And you know how to draw a cube, you know, so you people there, you are practical people, so you should know what a concrete cube is. You see this thing I'm drawing, it will take someone like 2 years to draw it anyway. So you have the 150 from here to here, you have here 150, and then you have from here to here also 150. I think we did test these things for lab, you know, so we have tested them, and the load that led to the crashing is this. And we all know that stress is force over area. It's the same thing. So compressive strength is maximum load over cross-sectional area. Area is what? Length times length. And then you get this. So after the crashing, usually this is for the analog type of machine. What they will do is that they will take the maximum load divided by the area, and they'll get the compressive strength. Remember, they have to convert to newtons. and then they'll get the compressive strength. So this is typically how it is done in the lab. After the testing, they have to do the calculation. But if you have the kind of the modern digital type of equipment, this calculation will be done for you. You don't need to do them manually. Okay? So this is just something to just show you, those who don't know, this is how things are done in the lab. Okay, so I don't think that there's much problem here, isn't it? So if, let's say, I give a question like this and somebody cannot do it, then okay? So my follow-up question comes, this question. 10 concrete cubes were prepared and tested by crushing and compression at 28 days in the laboratory. The following crushing strength in Newton per meter square were obtained. So just like I showed you in the first one, the calculations were done, and these are the results. We are to determine the characteristic strength and design strength. We have to take material safety factor to be 1.5. So today, I want to illustrate to you typically how we calculate for characteristic compressive strength. So if you see lab test result and then you are using C25 and the result are C25, C24, C27, and can say abroso and so ye cry until that calculation will be able bra and so ye. Okay. As you know, my rules, I don't go over things until you are specific. Going over is equal to overall shoe or the whole shoe. And me collapse. But if you are specific, I would also be specific. But overall, the whole shoe there, Allah, me collapse here towards this year. It's a class 9-1. Hey. Okay. So this question, what are we to do? We have been given compressive strength out of a laboratory test result, and we have to calculate the characteristic strength and design strength. And these are typical questions you can even get in exam, right? Okay, so from the question, how many samples were tested? The result, if you count them, is 10. So the N is 10. What do we need? Characteristic strength and design strength. So first of all, we'll look at how do we calculate characteristic strength. Okay, good. So let's proceed. So if you want to calculate characteristic strength of concrete, the first thing is you have to calculate the mean strength. What are we doing? If you remember, Fk, okay? Fk is equal to what? Fm minus 1.64 S. This is the formula I gave you. And we say the FM is the mean strength. This is the standard deviation. So we need the mean and the standard deviation to be able to calculate for the characteristic strength. So if we are calculating the mean strength, it's easy. Add all and divide by the total number of samples. So if they give you 10, like we have, we add all the strength, we divide by 10. If we are dealing with 100 test result, add all, divide by 100. If we are dealing with 30 samples, add all, divide by 30, then you get the average. The mean strength is the same as average strength. Stephanie? Okay. So this will give us 30.60. Now, what else can we do? We need to calculate our standard deviation. No be so. So the next stage is standard deviation. And if you remember, do you remember this was the formula I gave in the previous slide? This is the formula for standard deviation, right? So you need X minus S bar is the mean, okay? So you have to list all the crushing strengths that have been given to you in the question. And this is the X. Then from the formula, you see that we have X minus S bar squared. So in simple terms, let us first calculate X minus X bar, okay? So the X is these values, S bar is the mean strength we calculated, 36.0, right? So this minus mean, that will produce this. Remember that it is not X bar minus X. No. It is X minus X bar. So you must write the answers with the various symbols or signs, whether negative or positive. Now the formula is saying this must be squared. No be so? So you just pick these values, each of them, square it and write the answer. Square it and write the answer. Square and write the answer. Square and write the answer. And then we get this. Then the formula was saying is summation what? X minus X squared. So we sum all this and we get 44.40. So our n is what? 10, isn't it? So this is a 44.40, 10 minus 1, the root. And this answer is this might be in Newton per mm square, right? So this is the standard deviation. Are we okay? This is a very simple computation. So this is the standard deviation. Then what else? We are almost true because the formula is Fk is equal to what? Fm minus 1.64 or so S. So we have got the values. So what else? What else can we do? What we can do now is to go and substitute these values. I'm clearing the screen. So remember the standard deviation is 2.22, and then the what do we call it? The mean or the average strength is 30.6. Okay, so now we come back here, we substitute. When you do substitution, voila, we get 26.96, so approximately 27. So the calculation we have done, the answer, the characteristic compressive strength is 27 Newton per mm squared. Meanwhile, okay, I'll come there. Then after you got the characteristic strength, we can ask you to calculate the design strength. So design strength, this formula has been given already, isn't it? So you substitute into this formula, the material factor has been given, and the design strength is what? 12 Newton per mm squared. Now, let's do a bit of analytical thinking here. Let me take this question. Manasseh.
Yeah. So
Yeah?
when we did the summation for all the 10 values which was given, we had 360 and we divided it by the total number of values. That was 10. If you get 36.
Okay, but I wrote something different, right?
Yeah,
I wrote 30.
30.6.
Okay. So it's kind of an error in the typo error. It's a typo error.
Okay,
Yeah.
Okay.
So that will be corrected in due course.
Okay. Thank you, sir.
Okay. So this is the typical thing we do. So when they give the lab test to me as a structural engineer, these are the calculations I have to do. And then now I will say that the results are okay. The concrete is fine. Let's proceed. You see the result we got here is 27. If let's say our concrete, okay, the design concrete, the design strength is C30. When you see the lab result like this, oh, baby, cry more than 30, no. See, only 3 results here are less than 30. All the rest, they are 30 or more. You say, oh, no. Meanwhile, in terms of characteristic strength, this result does not meet C30. So it means this answer that we got to be 27, if let's say our concrete strength required for the work is C30, it means this result has failed. we have to do new ratio and go and test again, right? If let's say our expected strength is C25 and we have got 27, great, it has passed. So we can now use that ratio for the work. So you see how it works. And so it's not just on the facial value, but it goes beyond that. And I believe if you have been given various values and all that, you should be able to do this calculation. Okay? Any question? Any question? Joshua?
Okay, yes, sir. Sir, good evening now.
Yeah, good evening.
Sir, please, I'm a little bit confused around the standard deviation. If you could take it once again, please.
Standard deviation is a formula. It's mass. Do you get it? So
Yes.
all you need is to look for the parameters in the formula and calculate. I just decided to put it in a table form to make it very simple to follow. But once it's a formula, it's a value minus the mean. You square it, you divide, and take the root. As easy as that. And I believe that it's not the first time you'll be doing standard deviation. You must have done it severally elsewhere. But the formula is what I want you to have right. And usually you notice that I prefer working in tabular form because it's the easiest way to follow. If you do it that way, it becomes so easy to follow. Okay. Okay, so I think the mean strength here is 30.6. So I'm not sure there's anything wrong with the calculation. There's nothing wrong. It's not 360. Okay. Unless, of course, you say I wrote 360 somewhere. Okay. I see it now. So I'll do that correction. Manasseh.
So, sir, so from where you did the type, when you got a typo error, 30.60 instead of 36.0, when you insert the 36.0 into the formula, your final answer is going to be 32.35.
No, let us first of all know that I do this calculation before I type into my slides. So typing here, there may be error in the typing, but may not necessarily affect answers.
Okay, sir.
What I want you to focus on is the process I've shown you. If there's error in the final answer, it should not constrain our learning. The procedure matters. Like I said, the teacher is responsible for the procedure, not the final answer. You got it?
Yes, sir.
Okay.
Thank you.
Right. So that's it. And then I think last year, similar questions were given, and still people were getting 0 because they can't even do this small calculation. Meanwhile, this calculation was also part of a coursework. You see, it's not fair. Okay, our last example, and then we end our class today. This year, you should be expecting a question in this particular line, where I'll ask you to do something similar to this as part of your question. So the figure below shows a typical floor layout. Calculate the ultimate design loads on the beams and sketch their loading diagram. And also calculate the ultimate beam load, ultimate design load on each of the columns. So it's kind of a 3-in-1. You do for the beam and the column. What is the information? We say the slab thickness is 150. Imposed load, which you're supposed to have gotten from the 6399, BS 6399, has been given 3. Superimpose their load, I believe you remember, 2.5. If you are looking at loads, look at the units. The unit matters. Meter square means area load. And then size of beam is 250 by 450. Size of column 250 by 250. Unit weight of concrete is 24, right? So now let's see. Just pay rapt attention and everything will be fine. There's no problem here. Okay? So first of all, let us, this is the plan, okay? This is the plan, right? This is the plan. And I believe you understand what green lines are. You understand what, I mean, I don't think it should be a problem. Otherwise, I'll be giving my account number to all the contractors in the class. I'm disconnecting my account now. Yami hu mobo and mamambi. What you say, amen. Okay, so you see that these big black are the columns, okay? Yeah, and all the black lines are the beams, right? So if you can see that clearly this beam here is a secondary beam. No be so. So if it's a secondary beam, if we are sketching this beam, you see that this one will be like this with a support, with a support like this, and then this beam will cut it, half comes here, half goes here, and it's going to be like this with a point load, right? Good. So usually in labeling of columns, we use the grid intersection. So you see that this is green line 1, and then this is green line C. So this column C and 1 are made, so we'll call it C1. We call it column what? C1. This one, C and 2 are meeting, so we call it column C2. Okay? And this one, for example, A and 2 is meeting, so we call it A2. Let us know that we prefer to write the alphabet first before the number. Instead of writing 2A, we prefer writing A first before the 2. Okay? And there's the universal case where we say, okay, C1, C2, C3, C1, those things are not there. But what I'm showing is the most basic form, as you already know on site. Stephanie? Okay. So now that you understand the plan, so you can see clearly that what is defined by the beam is what we call the slab panel. So let's say the slab panel 1, slab panel 2, and the slab panel 3. So if you look at this slab panel 1, you see the shorter side is 2 meters, isn't it? And the longer side is what? 5 meters. So K is equal to what? Ly over Lx. That's what we know. So that will be what? 5 over 2, isn't it? So 5 over 2, what do we get? 2.5. Okay? And that's greater than 2. So this is what? 1 way. And look at this. This is the shorter side. Okay? So this line I'll draw should align with the shorter side, isn't it? So if I take this second one, okay, what's the longer side? 6 meters. The shorter side, 2.5. Okay, so if we calculate the K, the longer over shorter, 6 divided by 2.5, 2.4 is also greater than 2. So it's what? 1 way. And this line must be in line with the shorter span, isn't it? Because this slab 2 and slab panel 3 are the same, is the same thing. So you have to identify the slabs and do this drawing within. Any question here? That's the most basic way. Any question here? Okay. So after we have done this, then what next? Then we know that after we have identified the slabs based on the classification, if it is 1 way, for example, slab panel 1, this is 5, and this is 2. The shorter side, this is the LX, so we divide this into 2. So all this load goes onto this. And then here, all this load goes onto this beam. Okay, so let's deal with here too. Let's say this one is also one way. So what do you think? The shorter side divided by 2? If we do this from here to here is what? 1.25. And from here to here, 1.25, isn't it? So it means that this load will come on this beam. And then this one too, similarly, this will come on this beam. Like this. So you can see that it's not difficult, right? So now you use this and then you decide on the load distribution. So if let's say you don't want to show all this shading, you can use the single arrow as I showed in the previous, maybe a big arrow like this to show the direction of the loading, if that's how you want it. That's also fair. Are we okay? Okay. So classification, load distribution. I think there's no problem, right? Good. So I want to clear the screen and then so this is the given, okay? What I have done, we have done this, right? So for simplicity, I have numbered all the beams. Is that okay? Beam 1, beam 5, beam 6, beam 4, beam 8, beam 7, beam 3, beam 2, and all that. I've numbered all the beams. Sometimes you can also use the green lines to show the beam numbering, but if you number it in this serial order, it's far better. Okay, good. So you see that this has been done. Yeah, this has been done. This has been done. So after you have done this load distribution, what you need to take note of is what we call slab supported area. In other words, we call it tributary area. What are we saying? We divided this slab into 2, isn't it? So it means that the whole of this is coming on beam 1. So we need to calculate this area and keep it. We need to calculate this area. This area will be what? This is what? 1 meter. So this area will be 1 times 5. This is 5 meter square. Isn't it? Now, it means that this white place is also 5 meters square. Okay? Then if you come to this particular one too, here. Here, the length here is what? 6 meters. And this one, from here to here is what? 1.25. So 6 times 1.25, 6 times 1.25 is what? 7.5 meters square, isn't it? So the white area here too is the same, 7.5 meters square. The same thing applies here. If you look at the mathematics very well. Then you do this. Once you do this, you are almost halfway through. Okay. All right. Then after you have done this, okay, then you have to remember that you need to calculate your design load. So all you need to do is you multiply your design load by these areas and you are good to go. And let us note here, the load, the beam itself has its own weight, which we call the self-weight, right? And then the slab, okay, remember we have the slab thickness like this. I hope you are following. And this is 150. And we also have the superimposed load, which is placed on the slab. Okay? And that one was 2.5. Man, this thing is misbehaving. 2.5 kilonewton per meter square. Okay? So, to make life simple, we take the slab across the beam, even though we know the beam should have been measured from here all the way to here, 450. But if you take the self-weight of the slab, you take everything across so that if you are dealing with the extra load for beam, it's just this small part remaining. If you take the full beam again, it's like you have done a double calculation, right? So you don't do it that way. So once you have taken the slab all across, if you are dealing with a beam, you are just dealing with this drop, not the full 450 beam again. Good. So let's quickly calculate the design load, which will now come and multiply with these areas. And then we draw the line diagram and we are good to go. Okay. All right. So I'm clearing the screen. I don't know if you want to take a screenshot. Okay. Okay. Zakari or Said.
Yes, sir. Good evening.
Yeah, good evening.
Please, when you were naming, you say this side is 6 meters, but when you were writing on the screen, you made it 7.5.
It's area. There is difference between area and length
Okay.
too.
Okay.
Okay, so the most easiest way of calculating the design load is what I want to show you here. When you are calculating design load, we looked about material unit weight, so that one should not be an issue. This time around, we are giving in kilonewton per meter cube. That's the weight of concrete. So because we want to get the slab load in kilonewton per meter square, it's easy. Just multiply the thickness of the slab. You must convert by the unit weight of concrete, 24, and then you get the slab load in kilonewton per meter square. And don't forget that the superimposed dead load is placed on the slab. Okay? So in terms of slab dead load, it's also a dead load. But that one was already given in meters, kilonewton per meter square. So when we add these two, we'll get 6.1. And this is the slab dead load. I told you self-weight and superimposed dead load, they are all dead load. That's what I said in our previous class. Okay. Then in terms of the slab, we have imposed load, right? The imposed load was given in the question. So to calculate the design load for the slab, we know that we have dead and imposed. So that's the load combination one, which is 1.4 GK plus 1.6 QK. So 1.4 GK and 1.6 QK, and we'll get 13.34. So fini? Remember, this procedure will not change. It's the same thing every time you are dealing with situation of this nature. Are we okay? Any question? So now with this, we have calculated the slab design load. We have calculated the slab design load. Okay. So if there's no question here, so remember that anytime you want to calculate the design load, you have to apply this formula 1.4 GK plus 1.6 QK. Then the next thing is we calculate the self-weight of the beam and the self-weight of the column, because the beam itself has its own weight. And column also have its own weight because we have asked to also do it. So for example, in this question, the B is asking us to calculate something on column. Do you get it? So it means it's important to also calculate the self-weight of the column. Okay. So when it comes to the beams and columns, it's important to let your answers be in per meter. Okay? It's important to let your answers be in per meter. So your answers being in per meter, it means, you see, I had already explained this drop thing, right? Because we have already taken the slab, and what is remaining is just what is in the bottom here. And we know the beam is actually from the top all the way to this level. The slab is 150, and the beam is what? 450. So the drop is what? The 450 minus the slab. Then we'll get this small part. If you take the whole thing again, it's like you have done it double. And that one, it means you are overloading the structure, which is not correct. So you don't take the same load twice and add it at separate place. No. So in this case, you just take the cross-sectional area and multiply by the unit weight of concrete. This one we know already. Okay? Then that answer should give you in per meter. And remember, anytime we are dealing with beam, column, the answer should be in per meter. But if you are dealing with slab, the design load you calculate, first calculate in per meter square, and later you can get your answers in per meter after doing some other calculation. Okay, so because again, this one, we know we have dead load and imposed load. The self-weight of the beam is dead load. And so we will apply 1.4 factor because this is dead load. And remember, you have done similar thing in design 1, so this is not too new. So to calculate the design beam load, 1.4 times this value, then we are good to go. Okay. As for the column size is what? 250 by 250. So this is in meters. So the area times the unit weight of concrete, we get 1.50. Then again, it's also a dead load. So we multiply by the dead load factor and we get design load. So you see this one that has been bolded, these are the design load. And once this is done, we have already calculated our area and we are good to go. Okay, so I'll show you typical calculation probably for one, and the rest is the same thing. So there should be no problem. Okay. Any question regarding calculating the self-weight? Because when you are designing, don't assume that the self-weight is 0. It is a comfortable assumption we do just for classroom, but in design, the beam itself has a weight, so cannot be assumed to be 0. I believe you did same in your steel design, design 1. That you calculate the self-weight of the steel.
Hello, sir.
Yes.
Yes, please. Sometimes when calculating the design load, in some book they multiply the load with this thing, the acceleration due to gravity.
That one, if you have been given in density, this one is kilonewton per meter cube. So this is unit weight, not density.
Okay.
Okay. All right. So now let us get this clear, the values we have calculated. The unit weight, design load for the slab, okay, is 13.34. Let's note it. And design load for the beam is 2.52. And design load for the column is 2.1. Remember, the beam and the column, the unit is kilonewton per meter, whilst that of the slab is per meter square. So it should tell you that you must multiply this with some area, right? But if you come to the beam and column, you must multiply with some meter, as simple as that. Okay? Good. So let's, before I show you the calculation, let's do one here, right? 13.34, can I remember? 13.34 and then 2.52, okay? So if we are dealing with the beam one, this area was calculated, isn't it? When we calculated, we had 5 meter square, okay? So the total load, and this thing is kind of trying to misbehave. Total load is equal to what? The 13.34. The design load times what? Area supported. My pen doesn't want to write. The design load times the area supported. And the design load is what? 13.34. If we multiply that by 5 meters square, we'll get the answer in what? Kilonewton, isn't it? So 13.34, okay, times 5, you get what? 66.7. 66.7. And remember, this will be in kilonewton. So after this calculation, you convert it to Newton per meter by taking this load. What is the span of this beam? It's from here to here, and that's what 5. So I'll just take this value and divide by 5. Then I'll convert the load to UDL. You see? So 66.7, if I divide by the span 5, I'll get 13.34. Okay? All right. Let us not forget that there's also a beam here. Okay? So now let's go and let me show you what has been done. So that's the slab supported area is what? 1 times 5, which is what? 5 meters square. Okay. Okay, so you see that beam 1. You see that the area supported has been calculated here. Do you see? 5 meters square. And the slab load is simply design load as the area supported. And this is what? 66.7 kilonewton. And because it's acting on the beam, it's more reasonable to convert it to what? Kilonewton per meter. In that case, I'll just take the span of that beam and then divide the total load by the span, and I'll get it to what? Kilonewton per meter. Right? And you remember the beam itself was what? 2.52 kilonewton per meter. So this can be done in 2 ways. Somebody may say, okay, first, this is the self-weight, and then I'll put a second load. This is the load from the slab. But because they are all kilonewton per meter, I have added them. But note that you can't add kilonewton per meter and kilonewton together. But they are all UDL, so I've added, and that is resulting in this diagram, you see. And this is the line diagram. This is what we have been analyzing in the past. So from here, we are able to generate this. Okay. Take note of this RA1. These are the grid intersections. C1 is the grid intersection. And then A1 is the grid intersection where the columns are. So in a similar manner, the same approach you do for all. You do for all. So the only one I may show here now. Okay. Is there any question anybody wants to ask? So at the end, when you finish, you have to sketch this diagram to show. Okay. You have to sketch this diagram to show. So, for example, if we go to this particular beam 2, do you remember this side? When we calculated This is the total area now on this beam, isn't it? This is the total area. So if we, this one, and then this one, this is 1.25. So, and this is also 1.25. Okay. I don't know whether it's my pen or something, but I will see what the issue is. So the area is simply 6 meters times 2.5, because 1.25, 1.25 is what? 2.5. And that will give us 15 meters squared. So if you multiply the slab design load by 15, we'll get the total load. Then we simply divide by the span of this beam from here to here, 6, then we get UDL. And then the other UDL is the beam web, which is also there because there's a beam. So in simple terms, look at what that also amounted to. This is beam 2, right? So you see this I was doing. Okay, this is a 50 meters square. So you see the formula has not changed. Slab load is design load times the area supported. And this gives us. So at all point, divide the total by the span covered by the loading, as we did in strength 2. You see, then that gives us the 33.35. Because I know the beam load is also UDL, and the slab is also UDL, I can add the 2 and get 34.19. Otherwise, you may decide to draw them separately as the self weight of beam and then the slab load. So it depends on you. So if you get here, this is what now you are going to analyze and get bending moment shear force. Stephanie? So if you remember, you see that this beam was a secondary beam, right? Which was resting on a primary beam. So in that case, you have to calculate the total load of this. So the total load is for this per meter. So total load is for 35.87 times 6, 215.22. That's the total load. Okay. So we'll end it very soon. We'll end very soon. Okay. So in this case, if I go to this beam, so this is what we had. The total load on this beam, right? Total load is a 215.22. So this is a secondary beam. So if I divide this load into 2, half goes to here and half goes here. Okay? So if I take this beam, you see that I can sketch it now like this with a support. Okay? And remember that this one, we divided this, and this going here, this one. So this beam is only left here hanging, only a beam. There's no slab here, isn't it? Then this load here will be placed like what? Point load. So the only thing we'll do is the beam self-weight, which is on this. Then you are through. Okay? So it's not a difficult task. So to crown it all, if we talk about column, it's the same thing. The beam you have done already, calculate the total, divide it into 2. So this beam, after you have finished, divide the total load into 2. Half goes here, half goes here. This beam, the total divided by 2, half goes here, half goes here. And this principle remains. Okay, you come here, the total load on this beam, you divide into 2, half goes here, half comes here. And that's the principle for the loading onto columns. And all of them have been shown beautifully in the slides. My focus is the principle, not really the heartbeat calculation, so that at least you can do it on your own. If you have any question, you can ask. So even before the question, so if you look at the beam on green line A, so you see that it will be like this. This column, okay, is a support. This column is also support. This column is also support. If you remember, there's no additional load on this beam apart from the UDL. I don't know if you remember. So it will be like this. Then this load that is coming here, when you calculate, you see that this place may become big, right? So okay. So if you have any question, you can ask so that we can end this class. Any question? So I'm just going to scroll through, even though the slide is already with you. So you see, this is the beam 3, and this is how the sketch look like. This is the beam 4. See, this is the beam on green line A, B7, B8. See how it look like? And then this one, see how this one to look like. And this is the column, the reaction from the various beams. And the calculation, as I've explained, is self-explanatory. Is that okay? Okay. So what I'll be expecting is that, well, this question, I don't need you to submit. You can solve it. These are practice questions. But this particular question, which is similar to what we have done, I want this to be an assignment. Let us do it. Please, I want us to do this and make sure, don't copy. You do as you understand. If you don't understand, ask for clarification. Make sure you are able to do this on your own. Okay? So this is a question 2-2 is an assignment you have to do and submit next week, God willing, when we meet face to face. So in a similar approach, you have to do this for this problem. Okay? I hope that this is not too much. Okay. If there is any question, you can ask. You can put your name and index number, which people have done already. But if you have any question or you want to share your thoughts, impression, right? Otherwise, we'll end the class. And I once again want to admonish all of you. It is very good to do something small before you come to class. That is what will help you to appreciate the course. You see, if you come to the class with no knowledge at all, it will not help you. And that will not be a good sign. I will try my best to explain, but if you do your part before coming, life will be far, far, far better for you. So this video will be posted and I'll share it. You can refer to any section that you think you need clarification, and then you can proceed. Please make sure you have gone over and again to understand what we have learned today, because it's going to form the core of the design. And then I think that there will be no problem at all. I don't think what we have done today is too difficult. The assignment, okay, this is the question. It's already in your slide, though. This is the question, okay? This is the question. All right. So since there are no questions, I want to thank you for joining the class, and we bring this class to an end in the name of God the Father, of the Son, and of the Holy Spirit. Amen. So thank you for joining, and I wish you all the best. Have a good time, and make sure you acquaint yourself with what you have learned, so that next class will be far simple. I know today's lecture is loaded, but it's for a good cause, you know. So just make time for it, and I think life will be easy for you. All right. So thank you, and then you can have a good night.